So the next bit, the last but one, digitization of video and MPEG. Particularly that MPEG is a standard we use for digitization of video. So that's what digitization of video, and particularly because there are a number of different types of digitization of video techniques are available. Out of that, we are discussing MPEG standard. Okay. So particularly this MPEG is moving picture experts group. JPEG, MPEG are the standards for compression techniques. Actually, MPEG. So first we'll start with the discussion of what video means, and after understanding the video signal, then we will discuss the MPEG. Basically, it is a complicated process. It is a complicated process. So anyway, we are going to discuss a simplistic interpretation of a complex processing of MPEG standard. Simplest interpretation. We are interpreting in a simple fashion, in a simple way, because each block itself is having a lot of internal complex software and hardware. So it's not so easy to discuss this MPEG in one class or in with the block diagram. That's what we are using, a simplistic interpretation of the complex processing that is present in MPEG 1 video compression standard. Actually, it's a video compression standard. So we are using that for digitization or A to D conversion. Okay. So the topic starts with related to correlation concept only, because when I want to do A to D conversion, in that A to D conversion, ultimately the bandwidth requirement is very important. With respect to that bandwidth requirement, I have to do the digitization in the form of less number of bits as possible, so that bandwidth required by the system is going to become less. So for that, a reduction in the bandwidth while doing A to D conversion, a number of techniques we discussed, PCM, and after that DPCM. So PCM is normal procedure. In DPCM, we take the difference of the two consecutive samples for encoding process or for quantizing process. So because of that difference, which is a small compared to the individual values, difference of the consecutive sample is small, so that the quantization levels are going to become less, and hence the number of bits in the code word is going to become small, or ultimately finally we can say it is a bandwidth required is going to be less by using DPCM or a PCM system. Anyway, PCM is a standard. PCM is a standard or basis for digitization. So that's we need to understand PCM system very thoroughly. The remaining versions are simply it is a improved concepts. Maybe DPCM, ADPCM, DM, ADM. They are the part of digitization. Similarly, the MPEG, JPEG, these all things are as a part of digitization along with the compression. Okay, so this MPEG, JPEG are related to compression than the digitization, because bandwidth concept always when I go for video signal digitization, automatically the bandwidth requirement goes to very high. So when it goes to very high, then I need to go for the compression of the video in such a way that digitized version is going to require less bandwidth compared to non-compressed form. So that is, we have a number of compression techniques. So no need to discuss about the compression techniques, because the topic now we want to discuss is digitization of video. Okay. So first of all, video is what? Video is what? It's a picture, visible, which we can see. Okay. So when a source produces correlated samples, discussed oversampling. I am doing oversampling in DM. With that oversampling, the adjacent channel, adjacent sample values are highly correlated. So means what? Highly correlated means what? There is a relation between the two consecutive samples in a huge amount, so that I can predict what is next. I can predict what is next because of the highly correlation. If it is uncorrelated, no way to predict. So this is I do sampling in such a way that oversampling, so that the samples are very close to each other. As the samples are very close, the correlation between the consecutive samples is going to become very high. So because of that high correlation, I can predict what the next sample, or I can make my quantization process staircase approximation almost your message signal M of t. So that correlation concept is very important. The word correlation we discussed in yesterday's subject. Okay, when a source produces correlated samples, so that means we do sample at the higher rates. That's all. Okay. A digitization scheme that takes advantage of this correlation can be more efficient compared to which is not using this correlation concept. That's what PCM and DM. You take the PCM and DM. So there is a single bit for each sample, single bit for each sample, whereas 8 bit for one sample in PCM system. So that is what the difference between DM and PCM in terms of bandwidth requirement. The change is what I am doing oversampling. Because of that oversampling, there is a high correlation between the consecutive samples, and with that high correlation, the approximation is very small staircase waveform. With that, I can go for less number of bits for each quantization level. So I think we have only two levels, either maybe plus delta or maybe minus delta. So that deviation will be represented by 0 or 1. So with that, the DM is more efficient in terms of bandwidth because of it exploits correlation between the samples. So in general, when the source produces correlated samples, digitization scheme that takes the advantage of this correlation can be more efficient. Okay. So now we will discuss how an analog video source efficiently converted into a digital. We discussed voice. We discussed voice. So next is what? How to make digitization of video. Analog video. Basically, when you take video signals, naturally they are in analog domain. So we need to go for its digital representation. Okay. Modern video compression techniques. Again, we refer to the compression techniques only. So based on that, we do the digitization process. Modern video compression techniques offer a way to represent video in an efficient and robust manner. On a simplistic level, video can be represented by three dimensions. That's what. Video means the video signal represented in three dimensions. Three dimensions. The two dimensions are spatial and one dimension two dimensions spatial and represent a still image that is two dimension 2D. Your photo, if you take it as a 2D and it is a still image, okay, two dimensions are spatial and represents a still image. Third dimension is temporal. Third dimension is temporal, spatial, temporal, and represents how the image evolves image evolves with time. It is a time based. First one is a standstill image, a 2D, a special dimension. A special dimension is representing a standstill image. The next one is what? A third dimension is a temporal, which basically represents how the image evolves with time. So image by image, actually it is. Your video is not basically a image by image. So it is with respect to time. So in this way, totally we can represent a video by 3 dimensions. 2 dimensions for spatial, which represents a standstill image, and another one dimension is a temporal, which basically represents the how image evolves with time. And next image by image, is going to act like a video signal. That's what, with respect to time, the evolution of image is a temporal dimension, and spatial dimension is a static. It is a 2 dimensional. Your image, your photo, is going to have only a spatial dimension. When you take a sequence of photo, you are adding a third dimension in the form of temporal, which is with respect to time. So at what time the first picture, second picture, and so on. Second image, third image, and so on. If these images are in sequence with a less gap, then it looks like continuous. So that is how we represent a video signal in its basic form. A 2 dimensions spatial that represents a standstill image. The third dimension is a temporal, and it represents how the image evolves with time. In practice, the still image, the 2D, in practice, the still image is actually represented further by 3 dimensions. One image, the still image, further represented by 3 dimensions. Represented by 3D. So what are 3 dimensions? The 3 dimensions are luminance and 2 chrominance. Luminance and chrominance. 2 chrominance. 2 elements as chrominance. Chrom means color. The 2 color parts, one is luminance. Luminance means brightness, intensity, brightness, color. So one image, a standstill image. If you take your photo is having luminance, your photo is having chrominance element. Luminance with the brightness. I think you are sometimes adjusting the brightness in your mobile. When you want to see image, you can adjust the brightness also. So by brightness element, so that image look is get changed. So that brightness, the luminance term is also one of the important component of a standstill image. And the other 2 components of the standstill image is chrominance element. Chrominance is color. Luminance means brightness. So what color with what bright? So based on that, your image is going to be. Okay. So finally, a standstill image can be represented by these 2. A standstill image. Third one is with respect to time. So luminance with a temporal parameter time. So the total is going to become a video. Because standstill image itself is represented by 3 dimensions, that luminance and 2 chrominance elements. 4th dimension is the time. So in this way, a video is having totally luminance, chrominance, and a temporal dimension. Okay, so these 2 chrominance and luminance, actually these luminance and chrominance are the part of analog video which is having RGB. When analog video is having a color in the form of primary colors RGB, red, green, blue. Those who studied drawing subject in high school, they know the meaning of primary RGB and the remaining colors are be taken as a secondary. And why we call RGB as a primary? So because you can generate any color by using the combination of RGB. So because of that, RGB is called the primary. So that the luminance term and luminance totally gives you what value of R and G and B are present in a given color. Because with the variation of these three in a appropriate fashion, you can generate any colors. If there is a different colors are there in image, actually inside that image there is some amount of R is there, some amount of G is there, some amount of B is there with the brightness. So that's what basically in analog the image is available in the form of brightness plus RGB. When you go for the digitization, after the digitization it is available with luminance and luminance. So now it is not the RGB. The provenance is a different concept compared to the color only, but the way of representation is changed. Okay. So we are discussing the image in terms of luminance and provenance. We are not discussing about anything with the RGB. It is only in analog domain. Analog domain, the videos are available with RGB concept, but in digital domain it is available with the luminance and provenance parameters. Okay. MPEG standard takes advantages of the high degree correlation of spatial and temporal. There is high degree correlation of spatial and temporal that is expected in a video signal. Yes, we expect. This temporal and spatial signals are highly correlated. So, in order to reduce the number of bits required to represent the video signal. Yes, if there is a highly correlated, if there is a high correlation, always we exploit it, we use it for the benefit of reduction of bandwidth. If there is a correlation, then no need to send individual, better you send in relation. In relation you send it. No, don't send it as individual. So it takes more. It takes more compared to the relative concept. That's what the correlation means. Yes, don't send the second signal as independent or second sample as an independent. For example, first one is a 10 volt, second one is a 10.1, next one is a 10.2, then the 10.3, 10.4 like this. Then these sample values are highly correlated. Means what? If I transmit first 10, second no need to transmit 10.1. Instead of 10.1, I transmit 10 minus 10.1. That is the 0.1 I transmit. The difference between these two samples I transmit. 0.1 I transmit instead of 10. Because as I am transmitting 0.1, it takes less number of bits to represent as compared to my 10. The same concept we are using, highly correlated means for the next sample value will have a lot of relations with the first. So as they are having a lot of similarities, then no need to send that similarity parameters as usual because they are similar. Only there is a small change, that change we need to transmit. Okay, so that MPEG basically it takes the advantages of high degree correlation of spatial and temporal that is expected in the video signal. Yes, that high correlation is there in the video signal in the form of spatial and temporal. That correlation is exploited or taken as an advantage by the MPEG standard. Okay, so that's what now we'll discuss. The simplest interpretation of the complex processing occurring in MPEG standard video compression technique. Okay, so take the MPEG block diagram. It is not possible to go in details of the MPEG in its simplest interpretation model. In its simplest interpretation model, we will discuss the MPEG standard. Try to remember this MPEG is a digitization of video. MPEG is a digitization of video. PCM is a digitization of voice. Even it is a general encoding conversion, but particularly it is used in voice digitization. MPEG is for video digitization. Okay. So let's some information I will discuss. Now we will discuss simplistic interpretation of complex processing that occurs in MPEG 1. Variants are there: MPEG 1, MPEG 2, MPEG 3, and so on. MPEG 1 video compression standard. So that's called MPEG system. In figure. One thing, this is what the very important note. The processing shown in figure 32 is applied to each of the three components separately. So what are the three components? What are the three components? The first component is luminance, the last two components are chrominance. So these three components are processed separately according to the figure 32. Whatever the blocks, whatever the processing steps we use in the figure 32, it is applicable for each of the components separately. And we are not sending total video as a one component, and we are not doing the processing in the MPEG standard, which is separately. This word is very important. Okay. I'll give you the MPEG standard block diagram. Video signal, image sampling, the image sampling, high picture, next. One frame delay, motion compression, sensitive picture. BCD quantization, then is equal to one encoding. The figures simplified of video signal processing. This one is very important. As you know, your video signal is having three dimensions. One is luminance, the other two is luminance, and the processing shown in the figure 32 is applied to each of the three components separately. Luminance processed separately, luminance processed separately. So that is one of the important, because I am not giving the entire image as a tag. So the components it's split into luminance and we extracted image, luminance and luminance features are extracted, then this processing is done over the particular parameter. Okay. So now try to observe this video signal. What actually we are doing? AD conversion. In the AD conversion, the sampling is first operation. Yes, we are doing sampling here, and then we are doing quantization and encoding. These three operations have to be written there: sampling, quantizing, and encoding. Okay. So now starts with the discussion of the sampling. Then we move this process. What actually we are doing here? Then we will think of discussion of DCT in details. You know, quantization and encoding is the process already discussed. Okay. So working. Slash operation. The starts with what? Sampling. The explanation starts with sampling. Then what are the things available for sampling the image? But we discuss sampling the voice signal. Then what is the difference between sampling a voice signal and image signal? Okay. So we need to just relative based discussion. Relative, because already we know about sampling process, but we discuss sampling with respect to what? A voice signal. Now we are doing sampling for image. The only thing is that operation is sampling, but the things are instead of voice signal, what is the image. So for this, what actually the things we implement in the sampling process. Okay, sampling a voice signal consists of a single sample per unit time. One sample. When I do sampling a voice signal, I get a one value per unit time. Okay, but a sample of a video signal is an n into m matrix. Sample is what? Sample is N cross M matrix of what? Of picture element. In short, PELS, pulse. PELS. Picture element in short we call as pulse. So it is a standard used in video. Instead of writing bit, binary digit. Bit is what? Binary digit. A short form of binary digit is bit. Similarly, in case of this video, picture element, in short, it is called as pulse. So, a sample is having n cross m picture elements, a matrix of size n cross m, and each of the element is what? A picture element. Each of the element of that matrix is picture element. This is what the difference would be voice sample and video sample. Voice sample only one value is there, one sample per unit time. But here it is a matrix per unit time. Matrix per unit time, not a one value, it's a matrix. Matrix is of what? Order 2 dimension, order m cross n. And each element of that matrix is pairs. We get after doing the sampling a matrix, not a single value. That is one of the important difference between voice sample and video sample. Okay, video signal is an n cross m matrix of picture elements per unit time, pulse per unit time. Sample value per unit time for voice, matrix of n cross m picture elements per unit time. I am getting a matrix per unit time. Here I am getting a single sample value per unit time. Okay, corresponding to a complete still image. This matrix of picture elements, this matrix of picture element is also referred as video frame. This matrix, when you do a sample of a video signal, the output of that sampling process of a video signal is a matrix of picture elements. That matrix of the picture elements is also called as video frame. So one frame you are generating per sample, per sampling. Within that frame, one matrix is there. Within that matrix, n cross m picture elements are there for a sampling of standstill image. Okay. In fact, there are three such frames must be obtained. In fact, there are three such frames must be obtained. One we obtain for what? Luminance or maybe a chrominance. Similarly, we need to go for another two. So the total is three such frames are required because you know your image is having or your video is having three components. It is made up of three components. The one frame what I obtained is for one component. Similarly, you have to do for another two components so that you are going to generate total three such frames. Okay, that is one of the important. In fact, there are three such frames must be obtained. One for each of the luminance and two for chrominance. So next we will discuss after generating the frame, what next? We generate the frames after sampling. What I am getting here? Frames. After getting the frames, as with voice signal, the quality of reconstructed video signal, the reconstructed voice signal, you know, it depends upon the sampling rate. Under sampling, reconstruction is not possible or the reconstruction is distorted because of the rising effect. So the same principles we are going to apply here. Only thing is that instead of voice, it is a video. Okay. As with voice signal, the quality of the reconstructed video signal also depends on sampling rate or frame rate. Because when I do sample, I get a frame. That's what it depends upon the sampling rate or generally called as frame rate. At what rate you generate the frames is very important. Again, it should be according to the Nyquist only. Okay, so that is at what rate you are generating the frames. However, this signal quality, reconstructed signal quality is also depends on the bandwidth required to transmit and store the signal. This also depends upon the bandwidth, not only sampling rate along frame rate. Along with that, it is also depends upon the bandwidth. So, if you give more bandwidth, you will get a quality. But bandwidth is a scarce resource, we need to operate in a proper way. So, MPEG standard takes the advantage of fact that human eye is less sensitive to change in chrominance than luminance. So, please, it is the behavior of your eye. It's the behavior of human eye. What it is, the MPEG standard takes advantage of the fact that human eye is less sensitive to changes in chrominance. The color, if the color changes by small, it's not possible to differentiate or identify. We are not able to differentiate. But, however, it is very sensitive to change in luminance. If the brightness changes, eye will identify easily. It identifies as there is a change. So it feels the change with respect to luminance compared to chrominance. So this is what eye is not able to. If eye is not able to, then why to transmit? If it is not able to differentiate, then why to transmit higher rates? Higher rates means what? Every element I am transmitting, even though if I am transmitting every element, but it is not identifying it. Okay. So that is what MPEG standard takes advantage of the fact that human eye is less sensitive to changing chrominance than luminance, and so uses lower frame rates for luminance signals. Uses 1 minute. There is a small disturbance. So there is a disturbance because of that. The students delay. They are doing some work in the somewhere hall. Okay. So that is ultimately what next? We are transmitting lower frame rate for chrominance signals. Lower frame rates. Rate means per unit time how many number of frames you are transmitting. Frame is what? It's a matrix of pixel elements which is outputted by a sampling process. Okay. Typical frame rates for luminance. Typical frame rate for luminance signals may range from 15 to 60 frames per second. 15 to 60 frames per second. The sampling rate or generation of frames of matrix M cross M is 15 to 60. Whereas the luminance frame rate is 1 by 4th of this luminance frame rate. 1 by 4 means what? If I do at 60 frames per second. So 1 by 4. 1 by 4 is what? 60 divided by 4. So it is 15 frames per second for 15 frames per second for chrominance. So means what? If I send 60 luminance based, then I send 15 chrominance based components of that video. So this is what exploiting. Otherwise, I need to transmit both at 60. Okay. At receiver, a decoder uses. Then means what? If I am sending it lower rates, then how I get back the things at receiver side. So we know the missing part will be connected by using interpolation function. We discussed in reconstruction of voice signal. Reconstruction of voice signals. Through the samples, we use the samples, we pass us through a low pass filter along with the sync function as an interpolation function. With that interpolation function, samples are approximately joined or connected. By the connection is in the form of interpolation function. So with that, it is possible to join the gap between the two consecutive samples. So the same thing at receiver side, a decoder uses interpolation function to construct the missing luminance samples. Because 60 luminance are there, 60 luminance frames are there, only 15 luminance terms are frames are there. But I have to make one full picture at one full video at receiver side. So that gap, 1 by 4 gap compared to the luminance is filled by interpolation function used at the receiver side. Okay. So the next, after discussing about this, next we move to M5 encoding algorithm. M5 encoding algorithm. So this part, this encoding algorithm. Next we'll move to the CT. I think the quantization relevant encoding is a procedure where we already discussed quantization we know. And again, depending upon the quantization levels, we go for encoding techniques. Particularly, we use run length encoding for in MPC 1 standard. Okay. So now we'll move to the another second part of this process is called as M5 encoding algorithm. It encodes the frame. It encodes the first frame. It encodes the first frame in a video sequence in the intra-frame coding mode. Intra-frame. As I indicates intra-frame coding mode. First frame. First frame by intra-frame coding mode. So that's what I picture is generated. I indicates intra. Okay. So it encodes the first frame in a video sequence in the intra-frame coding mode that I picture generates. Then each subsequent frame, next frames, is coded using inter. Then these are INTER. Inter. Intra means within. Inter means out of. It takes one frame and within the picture elements, pulse within that matrix, takes another elements and it do the correlation finding, it finds the correlation between picture element in that matrix and it do encoding of that. Users exploits the correlation of sample values, not the frames. So it do that intra-frame coding mode. Intra means within the frame. What within the frame? The picture elements are there. So it uses that picture elements and it do the coding process by exploiting the correlation concept itself. But the correlation is between picture elements, not between the frames. Once it completes the intra-frame coding mode for first frame, the next frames present in the sequence of video sampling are going to coded by inter-frame coding mode, which generates the picture. Inter means what? Already it is having iframe. So with respect to this frame, what the changes of next frame? So that relationship it exploits and then do the coding procedure. So that's what P picture generated by using what? Already I or P is there based on that, based on referring to that or with respect to that, the next frame may be coded. Whereas the first one is by intra, remaining or by inter. Intra means I picture, inter P picture. I picture, P picture. P is generated by what? Previous, there is already one frame. It is already coded. With respect to that, what is the change in the third, fourth, fifth, sixth frames? That totally it is generating a P picture. Okay. So one is what? It encodes the first frame in a video sequence in the intra-frame code mode. Then the subsequent frames are coded using inter-frame prediction. That is a P picture. Where the previously coded I or frame or I or P frames are used for prediction purpose. So I already having the one frame. It may be encoded by using I or maybe encoded by using P. So after doing this encoding process, next frame I am going to get. When I take this frame, so with this frame and with the already existed I or P, I predict something with respect to the next frame, and based on that I do the encoding. I am not doing independently. Relative to that, is there any change? The changes are only encoded, but similarities are there. It will be sent. It is sent as 0. Okay. So that's for the first frame, the DCT is applied to, when I take the eye, first it will be taken as the eye. After taking the eye picture, this eye picture is applied to the DCT. After understanding this eye picture and P picture, the next is what I am doing, DCT on eye pictures. So now we will discuss about the role of DCT, because it is one of the important and common procedure in image processing, in the video processing. So please try to concentrate on the DCT role. So first I am doing DCT on eye picture. So first of all, what is the DCT? So the DCT, the first frame, for the first frame, the DCT is applied to each 8 cross 8 block picture elements. Usually your frame is having A11, A12, so A21, A31 up to AN1, and here it is ANN. This is what the N cross M, where N is in N and M. So N, M. Matrix is available as a output of sampling process, and then I do encoding of this by using what? I4, or I generate I picture by using I intra-frame encoding procedure. Once I do the encoding, the next part is what? I pass this I picture. So after encoding, I generate I picture. So once I generate this I picture, this is given as an input to the DCT. When I give this as an input to the DCT, I am not giving entire frame as an input to the DCT. I go for segmentation of this frame. I go for segmentation of this matrix. So what is segmentation of the matrix of this frame? So instead of giving entire frame, because it consumes more time or makes the complexity of processing. So to avoid the complexity of the processing in DCT calculation, I use 8 by 8 matrix. I use a one small submatrix of this, a size of 8 by 8 as I input to the DCT. Then DCT will calculate or operate on that matrix, and it is generating some elements. And after completion of this, it will go to the next submatrix. So this total matrix frame is divided into number of submatrix. The submatrix is given as an input to the DCT. Discrete cosine type transform. The cosine transform. Okay. So next is what exactly the meaning of DCT? Why we do DCT? It's very important. How we do DCT is not possible to think on board. So because I need to understand why to do it and what is the meaning of DCT is very important. Okay. For the first time, the DCT is applied to each 8 cross 8 block or submatrix of pixels. So mathematically, this 2D transform is defined by this DCT, direct cosine transform. Mathematically, there is one equation for direct cosine transform. That equation is important as a part of description of MPEG. Okay. Mathematically, this 2D transform, that is the DCT, is defined by is defined by x k1 comma k2 is equals to summation of m1 equal to 0 to m1 minus 1 and m2 equals to 0 to m2 minus 1 x m1 comma m2 cos k1 pi by m1 m1 plus 0.5 into cos k2 pi by m2 in bracket m2 plus 0.5. Equation 58. So this is the one equation by which we are able to calculate the direct cosine transform of the input picture elements in the form of 8 cross 8 block. Even though input frame is very large, but we are not giving frame directly as the input. So the frame is divided, segmentation takes place. Segmentation of frame. So segmentation of frame is where frame is a matrix of m cross n is divided into small matrix of order 8 cross 8. That small block is given as an input to the DCT. Then the small block picture elements are further calculated their corresponding direct cosine transforms. So this then the question is what the importance of this DCT? Why to find a DCT? Because we don't know anything about the DCT. We know quantization, we know sampling, and we will discuss something about encoding process, how that frames are going to be encoded. So after discussing this encoding, the remaining part of this explanation is the DCT and quantization we know, and we know the encoding operations in general. Only thing is that here how we do quantization and how we do encoding, particularly we do by using run length. How what is the meaning of run length we need to know it. But here it's not possible to explain how the run length is going to work. Anyway, only we are using run length type encoding for MPEG standard. So now I want to explain you about the DCT. Why we do DCT? DCT means what actually? Okay. Where this M1, M2, I am using M1, M2, K1, K2. Where this M1, M2 are the coordinates in the spatial domain. M1, M2 are the coordinates in the spatial domain, and K1, K2 are the coordinates in the transform domain. They are the coordinators in the one domain to another domain. And for 8 cross 8 transform, M1 equals to M2 equals to capital M1 and M2 is equals to 0, 8, M1 to 8, and K1, K2 range from 0 to 7. For 8 cross 8 transform, M1 is equals to M2 equals to 8 because your matrix is of 8 cross by 8 cross 8. Okay, K1, K2 range from 0 to 7, 8 elements totally. Pixels, what pixel I want in that 8 cross 8? Is it I want a first element, second element, third element, or the first row, second row, third row? Because totally 7 rows, 0 to 7 rows, 0 to 7 columns. So which element I want, depending upon that, K1, K2 is going to select the particular sample pixel elements from the 8 cross 8 block submatrix. Okay. So this is about the equation. Next is about the DCT, the direct cosine transform. So the DCT is closely related to DFT. DCT is closely related to DFT. What is DFT? What is DFT? Discrete Fourier transform. Okay. Discrete, you know the general meaning. FT. Why we do FT? FT for what? FT to get frequency component. Fourier transform. It gives you frequency components. That's what. DCT is closely related to DFT. The reason for applying the DCT is that it accurately identifies the spatial correlation of the picture elements within the 8 cross 8 block. Okay, what it is doing? The DFT is what? It is accurately identifying the spatial correlation of the picture elements within the 8 cross 8 block, which is similar to Fourier transform that identifies frequency component of a signal. Similar to that Fourier transform, this DCT is also going to find the, or it identifies the spatial correlation of the picture elements within the 8 cross 8 block, which you give as an input to this DCT as a submatrix. It finds the correlation, spatial correlation. So that if I know that correlation, then I can do that quantization with a less number of quantization levels. Exploit the correlation so that the quantization becomes simple. If the quantization becomes simple, I can go for encoding with less number of bits. So in this way, we can do a compressed video signal by using MPEG standard. So with this, the concept of MPEG standard as a part of compression and as a part of A to D conversion of video signal is a complete. In the next class, we will discuss another one, vocoder, as an application of A to D conversion process. So, is there any doubts? Okay. There is something about the DCT. In the textbook, they have given the expanded information about the DCT. I think it is not so easy to understand for the fifth sem students because we need to know a lot of information related to a DCT process so that it becomes very easy for us to compute how that DCT output is going to be present. Anyway, the MPEG standards are available in the form of level 1, level 2, level 3. So usually we are transmitting the rate of MPEG standards offers very video qualities at the level of 64 kbps to 10 Mbps rate. So when we are transmitting video signals to you, it is a MPEG standard. The transmission rate varies from 64 kilobits per second to 10 Mbps. So with this rate change, only we are giving you a quality of video. With this rate, we are giving you a quality of video. So video signals. Only you decide depending upon the available bandwidth. With this, that MPEG standard completes. The next class we will discuss a vocoder, which is the last bit. I think Monday I will engage for that vocoder concept. With that vocoder concept, the entire syllabus completes. And the last two modules are for IA3, Module 4 and Module 5.